So it's another tree problem as the daily problem. You can pause to read it. But the idea is we're starting out at the top of a tree represented by node 0, and we're given it sort of as a list of edges, so sort of more in graph form. And the idea is we can travel either way, so it's sort of this undirected graph that follows a tree structure, which means there's no cycles and everything it branches off from one central node point at any point in the tree. And we're given a list of nodes that have apples, and we want to find the minimum distance to, or time, but in this situation it's synonymous, minimum distance or time to collect all of the apples. So this is another problem that's slightly more complicated than the last couple days, but it's yet another tree problem that has a recursive or iterative solution. I'm just going to breeze through a recursive one. I don't care that much about optimizing or getting super in depth about more time complexity of this and stuff. It's probably going to be O of log n space complexity, and it's probably going to be O of n time complexity, because you kind of have to travel through on the order of every node, and it's log n space complexity because at any given point you're really only storing the current path from the base node to the current node. So that's going to be at most the height of the tree, which is log base 2 of the size of the tree. Anyway, the first thing we're going to do is we're going to change this input format into an adjacency list. So I'm going to say something like adj equals default dict list. And this sort of thing, after a certain number of times, you get very used to typing the exact same thing over and over again. And then we'll say for u comma v in edges, adj at u equals dot add v, and then the same thing the other way around. And I'll talk more about that in a second, because we actually kind of do want this to be directed. If we're looking at 1, we don't want to just say it's connected to 0, 5, and 4. We want to say, well, its child nodes are 4 and 5. That's the way that I'm going to kind of think about this. That's sort of what this function is going to look like. I'm going to define a recursive function here, so I'll call it traverse. And it's going to take a given node, and it's going to return, let's take 1, for example. It's going to return the total distance you need to travel to everything below 1 to collect all the apples below 1. So this should return 4. You go once to 4, back to 1, once to 5, back to 1. And that's eventually what we're going to call in the end, is just something like return traverse 0. So now that we have this, my sort of cool idea is that what we're really going to do is we're going to say something like, let's start with, we'll have dist. That's what we're going to return in the end. So we'll say dist equals 0, and then in the end we want to probably do something like return dist. And the idea that I think is like makes this a little bit sleeker is that there's going to be a certain situation where we return -2, and then what we're going to do is we're going to see, like, for example, the 0 to this 2, anything that happens after this 2, or the 0 to this 1, any distance that this travels, the 2 travels a distance of 0 past itself because there's no apples below it. We're always going to return at least 2 because we have this path going towards and this path going away. Similarly with 1, anything going on down here from 0, we're just adding 2 to that. But in a situation like 2 to 3, we don't really want to add 2. So if we called traverse on 3, what it's going to return, what we want it to return is -2. And then 2 is going to say travel there and travel back. So add 2 to whatever this returns, which is -2, so it cancels out. That's kind of the idea I'm going with here. So we're going to have something like if something return dist, otherwise return -2. And then here we're just going to say, let's say for child in adj at node. So we're looking at all the node's children, and then we're going to say dist plus equals traverse the child. So whatever distance the child returns, dist is going to be that plus 2. So if this returns -2, that means that that child is not ever worth traveling through, like this 2 to this 3. So it's going to return -2, it cancels out. If it's something like 0 going to 1, then 1's going to return 4, and then we're going to add 2 to that because we have to travel to there and then back at a different point. What else do we want to say? We want another situation where if we're... actually, I think this is pretty much all we need for now. We want to say here, well, a situation where we don't return -2 is either if there is some sort of distance, like this 1, there's going to be the 4 and the 5. So if dist, aka if this doesn't evaluate to false when it's cast to a Boolean, so aka if it's not 0, or if has apple at node. So like this 0 to this 2, distance from 2 to anything below it is 0, but 2 is an apple, so we want to actually retain that 2 here, this extra pathing of 2 from 0 to 2 and 2 back to 0. And then the other thing that we need to actually look out for is that right now for child and ADJ at node, like if we're looking at this 1, we want it to go to 4 and 5, not back to 0. Same with this 2, we want to look at 3 and 6, not 0. And 2 doesn't really know, it just has these 3 connections, 3 elements in ADJ at 2. So we want to somehow counteract that, and it's relatively simple. I mean, there's a couple ways you could do it. You could prune it. You could make a prune function that goes through and counteracts it, but we could also just pass an extra variable here and say, actually, let's just pass in yourself as the parent. So when 0 is checking 2 and then traverse at 2 is executing, then we know, well, the parent is 0. And then we can just say here, for child and ADJ at node, if child is parent, continue. And then the final thing we need to do, oops, these should be append. You could have this be default dictive set, and then you could use add, and actually I was fiddling around with this earlier, having this be a set and using add makes it a lot easier to trim if you didn't pass parent as an extra variable here, but passing parent is less complicated and less time consuming. Oops. Okay, so then here, now we need to correct this traverse and say, what would we want 0's parent to be? We just need it to be anything that's not in edges. So, for example, if we set it to be 2, that wouldn't be good. If we set it to be 1, that wouldn't be good. If it was 3 and 6, 4, and 5, wouldn't really matter, but we still don't want to run the risk. So we could have it be n, we could have it be -1, just anything that's not in the range from 0 to n. So here we have a situation where everything is false, and this is the final thing we need to correct for. When everything is false, we're going to return -2, because that's sort of the way that we've designed this function. We return -2 with the expectation that some previous recursion of this function is going to add 2 to it and have it cancel out. So here we just want to say max of 0 and traverse of this. We don't want to add 2 to it, because in a situation where there is, like this example, a solution where there are apples, it's not entirely false in the input. There's no need to account for this -2. So there it goes. Does pretty well. I mean, actually, it does pretty average, I think. But that's a pretty simple solution. This is kind of an interesting problem because it's a tree problem, but it's also given to you as a graph problem. So it's a great way to get your toes in the water as far as graph problems go, because those can be quite daunting.